Okay, so welcome everybody. Welcome to the first the colloquium series of the semester and of the school year. Um, uh, Compass Project and the physics department is happy to welcome Enrico Ramirez Ruiz to give a talk. I just before I go, I give the intro and I allow Enrico to start giving his talk. I just want to remind everybody um, how the questions are going to work. So we asked that most questions are at the end of the talk. Enrico has agreed and is to take talk or questions during the talk if there's something pressing. I'm happy to facilitate that, but we ask you to please raise your hand. And this is also true for at the end of the talk. You know, through Zoom, there is a raise hand button that you should see at the bottom central console. Please use that, and then I'll call people in the order at which we get them. And that's the way that we'll facilitate that. Thank you very much. Great. Okay. So I repeat again, the physics department and the Berkeley Compass project specifically, we have asked Enrico to come and give a talk, and we're very happy that he's here. Enrico Ramirez Ruiz is a professor at and the Vera Rubin Presidential Chair of Astronomy and Astrophysics at the University of California, Santa Cruz. He is also the director of the Theoretical Astrophysics Santa Cruz Institute and the Niels Bohr Professor at the University of Copenhagen. Copenhagen, not sure. After studying at the University of Cambridge, he was the John Bacall Fellow at the Institute for Advanced Study in Princeton. Since joining UCSC in 2007, Ramirez Ruiz has won a number of national awards for his research, including the Packard Fellowship for Science and Engineering, the Kavli Fellowship for the National Academy of Sciences, among many, many other accolades. Let me see, in 2011, he was named among 40 young rising stars in Silicon Valley and was elected a member of the Mexican Academy of Sciences, un orgullo mexicano for me specifically. Where he remains, by the way, the youngest scientist ever to be elected. In 2020, the NSF recognized him as one of 8 Hispanic scientists and engineers at the forefront of US research and was elected to the American Academy of Arts and Sciences. As the director of the LAMAT Institute at UCSC, Ramirez Ruiz works vigorously to support the promotion and protection of women and historically marginalized individuals in STEM. And by the way, I just learned today from one of his former LAMAT students, LAMAT is Maya for stars, I believe, which is amazing. I love that. Professor Enrico Ramirez Ruiz is at the forefront of developing the conceptual framework needed to understand the violent and capricious nature of the universe. And we are very happy to hear about it from him today. With that, I hand it over to you, Professor Enrico Ramirez Ruiz. Welcome.
Thank you, Cesar, for a wonderful introduction. Thank you, Compass, for all the work, amazing work you do, and for inviting me to give this talk. So let me share my screen. Wonderful. You let me know if you cannot hear me. I'm assuming you will. Okay, so I'm going to tell you about cosmic alchemy, particularly in this exciting era of gravitational wave astronomy. I'm going to touch upon a lot of the work that's been done in close collaboration with grad students and postdocs, which should be recognized. Let me give you a little bit of an outline of what I'm going to talk about. So I'll give you hopefully a pedagogical introduction of nuclear properties and the R process in particular. So we can center our discussion about what we mean when we talked about the R process. I'll talk about abundance observations in stars, so the sort of clues that we know about the assembly of these very heavy elements from spectroscopic observations of the sun and or nearby stars, which serve as a fossil record for chemical evolution and nucleosynthesis evolution in the universe. I'll talk about general astrophysical sites, and I'll touch upon neutron star mergers as a side of our process nucleosynthesis. And as you know, I'll talk about the clues that we have garnered since the amazing detection of GW 170817. And as you know, Dan Case and your colleague there, as well as Rafaela Margutti there, have driven a lot of the work there. So I'll talk about some of the lessons that we have learned. Then I'll talk about what we know about chemical evolution and the imprints of how these elements are assembled. And ultimately, I touch upon actually how planet habitability is actually essential. The amount of our process, nucleosynthesis, that ultimately make up to our own solar system are really, really important for planet habitability. And I close on that note. So for astronomers, this is our periodic table. This is the abundance distribution of the sun. The first thing that you should notice, there's of course the odd even asymmetry, where basically even nuclei are certainly more abundant. There's of course immediately clues that we know from nuclear physics. What I'm showing there is the closed neutron and proton shells. And as you can see immediately, the abundance peaks correlate with these neutron and proton closed shells, which of course we'll talk a little bit about their nature. Another important aspect of it is as you go beyond the iron group, particularly iron, which is the most bound element in the universe, you start requiring for stability a larger proportion of the number of neutrons. No? For example, you look at lead, which is doubly magical. You can clearly see the large asymmetry there between the number of neutrons and protons. Something that I want to highlight today is the formation of elements above the iron peak. Those are almost exclusively made by neutron capture. We usually divide them into two categories. As you know, when you capture a neutron, you beta decay, you become radioactive. If the time scale for the decay is much, much longer than the neutron capture rate, we call that the slow process. So you're basically capturing neutrons and then beta decay. And the rate at which you capture neutrons is actually slow. That's what we call the S process. However, for the R process, you have to capture neutrons at a faster rate than the beta decay, and that's what we call the R process. Something that I want to highlight there when you look at the abundance pattern, and hopefully I'll give you some insight as to how that arises, is that the peaks of the S process compared to that of the R process seem shifted. If we go back to those peaks, usually because the S process happens very close to nuclear statistical equilibrium, the peaks basically correspond with these neutron closed and proton shells, while the R process at first sight seem not to. And we'll talk a little bit about why is it that the R process peaks seem shifted to the left. And to do that, I'm going to spend a little bit of time showing you this very illustrative and pedagogical plot where it's shown the number of protons in the y-axis and the number of neutrons in the x-axis. The first thing that I highlight there is the stable nuclei. So of course, if you are basically capturing neutrons very close to equilibrium in the beta equilibrium valley, which is that black stable nuclei, you capture a neutron, you beta decay, you then capture a neutron, and you're very, very close to stability. What is interesting, and it's highlighted there, what happens when you capture a neutron and you beta decay and how you move. Now, what I want you to envision is if you are a stable nuclei and you sort of go vertically down, you start moving away from equilibrium, and the beta decay timescales start to be significantly short, all the way to the scales of milliseconds. And of course, the lifetime of these nuclei are actually relatively brief. And this becomes incredibly important because if we focus, for example, a standard R process pathway to make the R process, which requires separation energies of a few MeV, you realize that it's captured really, really far away from equilibrium, and that the timescale have to be incredibly prompt, of the orders of tens of milliseconds. And you immediately are led, as an astrophysicist, to think about, well, what is an object whose dynamical timescales is of the order of tens of milliseconds? It's a neutron star. And therefore, the viability, the astrophysical viability of models of the R process involve neutron stars, either two neutron stars merging or a neutron star newly born. after a core collapse supernovae. So another important thing to highlight here is the magic numbers, the closed neutron shells. And I'm going to just give you an idea of what's happening in those closed neutron shells. So the way that I want you to envision is that you're capturing neutrons. And as soon as you close those, you basically go through those closed neutron shells, the capture rate drastically decreases. And so why that's the case? So in order to illustrate what happens in these magic numbers, I show you here the neutron capture cross-section of nuclei in the S process, but it's with neutron separation energies of about 25 kiloelectron volts. So the first thing that you notice is that odd mass numbers tend to have higher cross-sections than even nuclei. And that immediately you start getting a hint about these odd even nuclear symmetry in the abundance pattern. But most striking, particularly there when you look at N50 and 82 and N126, you see the substantial lowering of the cross-section near the magic numbers. Why? Because those nuclei are stable, they don't want to capture neutrons. And as a result, there's a substantial lowering of the cross-section. And as a result, abundance should anti-correlate with these N capture cross-sections. So the way that I want you to envision is that you have this neutron flow, and that neutron flow stagnates in these magic numbers. The abundance increases specifically there before you're able to go through those barriers. Another way to visualize it is you can imagine the neutron flow as cars in a highway, and if you have an accident, you get a pileup. And that's exactly what's happening here. You get a pileup, and usually we refer to the first, second, and third peak at the position of these magic numbers. So I'm just going to highlight here that if you're very close to equilibrium and you're capturing neutrons, you basically cross, the first peak, as you can see there encircled in black, then the second peak, and then the third peak. And that's usually what we refer to as the first, second, and third peak of the S process. However, for the R process, because you're capturing so far from equilibrium, you actually cross those magic numbers very, very far from equilibrium. And by the time you go back and beta decay, you basically lost memory about the exact neutron number in which that was reached. So as you can see there, the first, second, and third peak in the R process are actually shifted to the left in atomic number. And that's because they reach these closed neutron shells far from equilibrium. And what you're seeing there is basically the projection of the beta decay slope onto the atomic number. So even though at first sight, when you look at the abundance pattern, it seems that these peaks do not correlate with nuclear structure, they do correlate, but you have to understand that they basically were assembled far from equilibrium. As a result, the neutron number in which that magic neutron number was reached basically gets eradicated as things decay back to stability. So when we looked generally at the abundance pattern, this is what you see. A few things are important to highlight is that, about half the elements above iron are made by the S process, half the elements are made by the R process, and that elements can be made by both. For example, you can look at lead, for example, which is, even though primarily an S process product, our process can actually contribute to a few percent of the total abundance of lead that we see in the universe. What you can see there also is the clear shift to the left of the first, second, and third peak of the R process. And you can highlight, for example, the third peak of the R process is my favorite peak because it has gold and platinum. And that peak in particularly is primarily made by the R process, not surprising because it was basically done far away from equilibrium. Now, it's also highlighted there europium, and europium is an incredibly important element because it has such a strong oscillation strength at optical UV wavelengths that we utilize europium as a way to actually measure the R process content of stars. And we use, usually when the spectroscopic observations are very high resolution, you can almost see every single element in the periodic table. But for the vast majority of stars, europium is actually our anchor in to measure the total R process content of stars, more broadly speaking. And as you can see, now, if you're intrigued, europium happens in the rare peak element, which it doesn't, at first sight, coincides at all with nuclear structure, and there's significant amount of debate of how that peak is made. But if you have questions, we can talk about that at the end of the talk. So what do we know about the R process in stars? Particularly if you like the R process, you like this star that it's highlighted there. It's usually called the Neutron star. And this star, even though it's very low metallicity, it has a very large relative abundance of something like gold or europium or R process. And it's actually, relatively speaking, the highest enhanced R process star discovered so far. Now, what we know from spectroscopic observations of stars that have really boomed in the past decade is that the abundance shape is actually incredibly robust. The abundance pattern is incredibly robust, particularly what we call the heavy R process, which is between the second and third peak. Now, what you can see here are low metallicity stars where the abundance actually has been shifted. So the x-axis has just been shifted so that you can actually see the pattern, and it's superimposed with the pattern of the sun. So ultimately, what we now know is that whatever made the R process, the relative abundance, we can see stars with large variations of the total R process contents, but the relative abundances of R process elements is incredibly robust. So whatever mechanism made the R process has been operating in an incredibly robust fashion. And that, of course, has relatively strong constraints for nuclear astrophysics in the sense that it should be relatively independent of the initial conditions, and somehow you are converging to this pattern that it's incredibly robust and has been operating, for the past 10 billion years or so. Now, what we know, and I just wanted to highlight this, and we'll touch upon this, which is actually incredibly important, is that even at a given iron metallicity, so what it's plot there is iron metallicity in log units, where it's all relative to the sun. So this is how astronomers plot. So 0, 0 is where the sun lives. It's at solar metallicity. And as you go to -3, it's 1 part in 1,000 of the iron abundance of the sun. And as you can see, around about 1 part in 1,000, they're highlighted these two stars that have very similar iron abundance, but they have almost a factor of 100 in terms of the R process content. So that's something that we notice and we'll talk more about, which is large RMS fluctuations of the total amount of R process that is locked up in the stars. Another important thing to highlight is only a few % of these metal poor and old stars show these clear R process signatures. So these large variation is incredibly important. So I just wanted to highlight what astronomers do. So this is basically zooming in a high resolution spectra. I want you to say, place your attention at the calcium K lines about, down to 4,000 angstroms. You can see that both stars have relatively similar amount of calcium. But for example, if you go and look at the europium line, a little bit short of 4,130 angstroms at the bottom panel, you can clearly see the large difference between the star that has significant amount of R process and that doesn't. And the depth of that absorption light feature is remarkable. And this gives you a feeling of how astronomers basically devise the total amount of R process contents in stars. Okay, in general, I wanted to give you some anchor points. So a good anchor point to have is like the Milky Way, it's forming about 1 solar mass per year in new stars. So about once a year in terms of total mass, about a solar mass of new stars come into the Milky Way. And that, that's an average star formation rate, which of course, if you multiply by the age of the universe, it tells you broadly more or less the total amount of stellar mass in the Milky Way. Now, to anchor this, in order to actually explain the R process, you need to actually produce about 10 to the -7 solar masses per year. This is a kind of magical number. So for every new star of a solar mass that it's made, you have to basically synthesize about 10 to the -7 solar masses per year. And 10 to the -7 is actually very close to the fractional mass of total R process mass in the sun, which makes sense. So we have these two competing sides, particularly 30 years ago when we thought this core collapse versus neutron star mergers. Core collapse supernova happens very common for cosmologically speaking once every 100 years, so 10 to the -2. order of magnitude per year per galaxy in a galaxy like our own. So you only have to produce about 10 to the minus 5 solar masses per event. While neutron star mergers, of course, are much rarer because you have to make not only one, but 2 neutron stars. Then you have to assemble these 2 neutron stars close enough so that they actually have time to merge in less than a Hubble time. And of course, they merge to the radiation of gravitational waves, which take both energy and angular momentum away from the system. So the standard order of magnitude calculation is that these events happen about once every 10 to the 5 years, so 10 to the minus 5 per galaxy per year. So they have to produce about 10 to the minus 2 solar masses per event in order to explain the total R process content of the Milky Way. So can we actually put relatively simple constraints on how much our process is made? And in fact, we can. And the argument is actually a relatively simple argument. So if you have any sort of explosion and you want to turn the ejecta, so you just freshly synthesize new metals, they basically, especially in the early universe, they interact with the hydrogen and helium, which provides the vast majority of the cooling. And in order to turn that gas into stars, you have to wait until it cools. And the fastest that it cools is what we call the cooling mass, which is highlighted here, which you have to sweep of the order of about 1,000 solar masses of hydrogen or so in the early universe in order to actually start cooling. And then you can say, well, how much metals do I need to put in a mass of about 10 to the 3 solar masses in order to explain, say, the europium over hydrogen abundance that I see in stars? And therefore, that gives me a minimum mass per event that I require, because of course, if I sweep significant more hydrogen, if I basically dilute further my freshly synthesized elements, then of course, the europium over hydrogen abundance will decrease. So that basically gives you a minimum mass per event that you require, which is a relatively simple and elegant method. And this is just to illustrate a simulation that even though a neutron star merger could in principle start incredibly asymmetric, ultimately by the time you sweep that much mass, the blast wave is incredibly spherical. And here I show a simulation where in red you see the R process content, and by the time you get to the cooling mass, the simulation shows that the explosion is rather spherical, and it looks very, very similar to a supernova explosion, and really the only thing that you carry is the amount of energy that was input. So then you say, well, I have X amount of R process elements, I dilute that into the hydrogen, can I actually get minimum mass constraints? And you can. And particularly, for example, this neutron star gives you some of the highest constraint because it's highly enhanced. And you immediately, by this simple argument, rule out that standard core collapse supernova actually can provide you with the necessary mass that you need, just because the amount per event that you need is about 10 to the minus 3 solar masses, which is significantly higher. So that what you require for core collapse supernova explosion. So what this points at is that the R process has to be produced incredibly robust, particularly between the second and third peak, and that it's actually incredibly rare compared to core collapse supernovae. Yeah, it doesn't happen very often, but it actually produces significant amount of mass per event. And these are really the conclusions that we derive just solely based on observations of low metallicity stars, that these heavy R process, needs to operate in an incredibly robust manner, and that you need these very, very unique conditions. Either if you assign it to a core collapse, it has to be maybe 1 in 1,000 of those core collapse has to have some unique conditions, or neutron star mergers, which basically fit the rate and have to produce, significant amount of mass per event, which is what you see and infer from observations. Now, I'm not going to talk broadly about the broad range of nucleosynthetic sites after a merger. This is being a slide taken for one of Dan Kaysen's, but I'm going to illustrate particularly how the R process is made in an incredibly robust fashion in the tidal tail ejecta, just to give you a feeling of the sort of necessary conditions that we have. And in order to do this, I'm going to show you one of the simulations I did for my grad school. So here is basically 2 neutron stars are about to become dynamically unstable. You get this steepening in the interaction potential. The neutron stars become dynamically unstable. You have mass shredding in the outer Lagrangian points. And about 1% of a solar mass or so, it's able to get above the escape velocity from the system. So what we're going to follow is actually the thermodynamical conditions of those tails, and we're going to basically see how the nuclear properties evolve. Now, these tails are incredibly robust for the R process, particularly because they get very little neutrino irradiation. So their composition actually remains rather unchanged. So generally speaking, I mean, the simulations from the ones that I show you, which were post-Newtonian, has drastically improved. Now we have full GR MHD calculations, and now simulations are getting to the point in which we're trying to do full Boltzmann transport of neutrinos. But in general, these tidal tails, vary between 5 times 10 to the minus 3 to 5 times 10 to the minus 2 solar masses, and velocities of tens of percent of the speed of light, which basically depends on the position of the outer Lagrangian points in the escape velocity of the outer Lagrangian point. So it depends on the mass ratio and also on the nuclear equation of state of the neutron star. So what we're going to do here is actually follow the nuclear evolution of the tails, just to give you a feeling of how the R process is actually assembled. And I apologize that some of the labels here are small, but what we're going to follow through is in red here at the top plot. What we're seeing is the temperature evolution of the material as it expands. So we're following these nuclear tidal tails. The density, which of course starts to plummet rather dramatically after the material starts to expand, and the heating rate, which is basically all of these decay products are heating these nuclear tails as a function of time. Now, something that I want you to highlight is the material is incredibly neutron rich. The YE that is highlighted there is 0.1. And in nuclear statistical equilibrium, you already have tons of neutrons, and as you can see there, clear nuclei, particularly around the first peak, as illustrated there in the abundance distribution. So what we're going to basically follow is the nuclear evolution of this with an R process network. So neutrons are basically being captured. You go first, second, and third peak very, very quickly. You form even very, very short-lived nuclei, and then you start decaying back to equilibrium. And as you decay back, the material is continuously heating by both, photons and decay products. And that actually keeps the temperature from really plummeting, as you can see there in the red. And ultimately, these decay is essential in powering the electromagnetic signatures that we see. And ultimately, as you decay back to stability, now we're about 10 years or so, you can clearly see the first, second, and third peak. They're clearly formed. Now, just to give you a feeling, I just chosen my favorite element, which is gold. Gold is about 6% of the total R process content, but it gives you a feeling of how much mass is actually produced just in the tidal tails. And it's about, a Jupiter or so, Jupiter mass of pure gold. And that's, of course, hard to wrap your head around it. But if you ask, one of these events can actually supply with the amount of R process or specific gold in about 1 million stars. And that becomes incredibly important, that these events are so rare and produce so much gold that you immediately start relating those large RMS fluctuations that you saw in the abundance content. And we'll talk a little bit more about that, thinking about turbulent diffusion of metals in the interstellar medium early on. Okay, so broadly speaking, what we have is the assembly of these mergers. So two objects, in this case, two neutron stars, they don't have to be of equal mass. Basically, they're assembled at a distance that is small enough that they're going to ultimately merge within a Hubble time. And that secular evolution lasts for about hundreds of millions of years to a gigayear. We talked about they become dynamically unstable. You get mass shredding in the outer Lagrangian points. If the mass ratio is not close to unity, you only have actually one tail. You produce basically our process as I illustrated, and what matters is the amount of mass and the velocity of that material. Ultimately, I'm not going to go into a lot of detail, but these materials basically heat up. So that fights against adiabatic expansion. It's decaying, and this decay heat actually is what ultimately powers the electromagnetic signature, which of course the vast majority of the photons are observed when the material is about to become optically thin, close to that, when the expansion time is comparable to the diffusion time. Okay, so something that I want to just highlight is that an important component that we have here to try to indicate whether or not our processes were made is actually the heating rate of these nuclei, the decay for this nuclei. And what I show here is some early calculations by Luke Roberts, who was a grad student at UC Santa Cruz, and showing, as was actually in fact predicted by Lee and Pachinski, the fact that you have contributions from so many nuclei at a particular given time, not surprising, the decay heating rate is actually a power law. An individual contribution of a particular nuclei is illustrated there in gray. So as you can see, at a particular time scales, there's tons and tons of nuclei that are actually contributing to the decay, and not surprising, you get a power law. But that power law is actually incredibly important because we expect the bolometric light curve to follow that heating rate. And this is exactly what we saw on GW 170817. I won't go into a huge amount of detail, just to illustrate that we detected the source following the gravitational wave signal, and we were able to monitor its light curve and infer its bolometric luminosity. I want to just highlight that I was incredibly lucky to be part of the group at UC Santa Cruz that discovered the transient, and that was led by Ryan Foley and his group. And as you can see, an incredibly diverse and early career group, and I'm really proud to be the oldest of the group there. Okay, so we can actually infer a minimum mass estimate just from the bolometric decay of the light curve. So how much heat, how much material do we actually need? And the answer is about 10 to the minus 2 solar masses or so. And that's the amount of our process material that you need in order to produce, in a calorimetric way, the total amount of bolometric light that we saw. Yeah, and therefore we get a fairly strict lower limit on the mass. And in general, I think those numbers that I gave you, that's more or less what we find, that the LIGO rate implies one of these events about 25 mergers per mega year, which is about 1 every 10 to the 5 years. The estimates that one derives from the total amount of our process mass, of course, you have to also convert the efficiency. It's about 0.06, very close to the 10 to the minus 2 numbers. Of course, 10 to the minus 5 multiplied by 10 to the minus 2 gives you the magic 10 to the minus 7 solar masses per year. If you multiply that by the age of the Milky Way, you get a total amount of mass in the Milky Way of about 10,000 solar masses of our process. A non-negligible fraction of that is actually locked up in the stars that we see today in the Milky Way. So that seems to be a feasible model. Now, something I wanted to transition to was really to talk about chemical evolution. And I wanted to put these kind of picture in your head that when you're thinking about type 2 sort of core collapse supernova products, something like alpha processes, alpha elements like magnesium, that happens in the Milky Way very, very, at a rates that are very, very common and produces little amount of mass. So I sometimes like to think about that model as a, chocolate cookie with a chocolate thin layer that is actually rather well distributed. While, for example, neutron star mergers, they happen, so rarely and produce so much mass that it's more like a chocolate chip cookie. So of course, when we're thinking about the early Milky Way, if basically you make stars very, very close to the chocolate chip cookie, in this particular case, as illustrated here by europium, then the stars that are made from that gas are highly enriched with europium. What if you're far away from the chocolate chip, then the abundance are actually drastically diminished. And you immediately start thinking about, those RMS fluctuations that we see in the abundance content are really correlated with how these metals are produced, the rate, but also how they turbulently mix in the Milky Way. And this is actually, very evident when you look at the RMS fluctuations of both, say, for example, magnesium over iron and europium over iron as a function of iron metallicity. So as you know, the universe basically increased in metal content as a function of time. After the Big Bang, we only had hydrogen and helium primarily. And then all of these stellar processes start to operate and increase what astronomers call the metal abundance of the stars. We measure abundances in logarithmic space, as I illustrated there. And in both of these, 0, 0 is where the sun lies. And what you can see is that the RMS fluctuations of alpha elements, something like magnesium, which comes from core collapse supernova, are rather small compared to the large abundance variations that we see in iron. And that's deeply correlated with basically the fact that you're injecting those metals much rarely, and that it takes a significant amount of time for actually the Milky Way to mix these elements. And that's exactly what we see in simulation. So what I'm showing you here is a simulation of a disk galaxy. I tried to illustrate that at the top, that we're looking at a piece of the Milky Way disk. You're making a cross section there. What you see, the contours are actually density of the disk. In green, we actually show alpha elements, so something like magnesium, and in purple, we show europium or R process elements. And as you can see, as a function of time, already supernova turbulent mixing in these small scale simulations where we're actually able to resolve individual remnants are clearly showing that magnesium is already relatively well mixed, while europium takes significantly longer. Why? Because the number of events entering in the Milky Way are small, and then the turbulence driven by supernova takes significant amount of time to basically mix those elements. If you take, a sound crossing time in the Milky Way disk, that's about 1 gigayear. And of course, we're turbulently mixing subsonically. So it takes quite a bit of time for, these RMS fluctuations to actually be eradicated. And what is actually quite interesting is that those abundances tell us something about the efficiency of turbulence driving and the diffusion coefficients of mixing of metals early in the universe. And this is basically what we see in simulations. What I show there are simulations trying to recreate a Milky Way-like galaxy. And what you see there are the highly enhanced stars that are R process rich from the simulations are actually highlighted as gold. And what you see is that there are not that many, but their variations are very, very large. And the question is, can we actually explain the large scatter that we see as a function of time in the Milky Way? And the answer is we can. So we, of course, tune some of the diffusion coefficients early on, but a lot of effort is now trying to really understand how these stars were actually made, and ultimately how the gas mixed and incorporated into new generations of stars in the Milky Way. And because our process is actually, happens rarely, it offers an opportunity to really understand some of these effects of turbulent mixing. Now, I wanted to highlight that even today at solar metallicity, we see variations in the europium content of sun-like stars. And the question is, does that actually has any bearing to basically us being here? And the answer is yes. So let me explain you. So a lot of the essentiality of life on Earth is actually deeply correlated with the presence of a magnetic field which protects us. And the magnetic field is made by a turbulent alpha omega dynamo, where the fluid convection currents are actually driven by radioactive heating in the interior of the Earth. And as I will show you, that heating is actually driven by our process heating today in the Milky Way. So the question is, are these elements essential to life? And this is basically what we pursue. Just to illustrate, this is the radioactive heating in the solar system. And at late times, what you see is that uranium and thorium, that ratio is actually quite important, if not the dominant source in the Milky Way, in the Earth about when it was about 10 to the 9 years. So about a giga year, as the Earth basically was made molten and started cooling as a function of time, where the generation of the magnetic field is coming. Uranium and thorium play an incredibly important role as a heating source, despite being, as we talked about, only small fraction of the total mass, but they contribute significantly with the energy. And potassium-40 also is an important contributor, although there's some argument that it doesn't find itself in the core as prominently as uranium and thorium. So these are the sort of calculations that Franz Nemo, a colleague of mine, we devised. And what we find basically is that at solar metallicity for sun-like stars, you can actually find a factor of about 3 in the total hour process content. So that means that the uranium and thorium can actually change by a factor of 3. So if we increase the uranium content and thorium content in the core of these models, we get more radiogenic heating, we get extreme volcanism, but the convection is driven just too vigorously for the alpha omega dynamo to actually be effective. So we expect to have basically no magnetic field. The Earth-like, simulations seem to put you in a kind of special spot in terms of generating both volcanism and a magnetic field. And if you actually have less radiogenic heat, what we find is that the Earth-like planet is basically able to produce a magnetic field, but it's in fact geologically dead with no volcanism. So then the question is, yes, maybe the amount of our process content is actually pretty essential to life on Earth. So I tried to, in 45 minutes that I was given, try to give you an idea that, yes, we believe that these are processes, the conditions are ripe in neutron-star mergers. There's a significant amount of debate as to whether neutron-star mergers were the essential for polluting material in the early universe, or where you need a type of exotic core collapse supernovae. But what we know is whatever produced these elements have to provide you an incredibly robust pattern between the second and third peak. And it has to happen incredibly rare and produce a huge amount of mass. And that is ultimately imprinted in basically our process contents of stars in the Milky Way, which we ultimately use to try to understand, how these metals basically diffuse through the Milky Way, mix, and ultimately led to less and less variation of our process material within the Milky Way. What it's actually striking is these events produce so much our process material per event that even one today in our own Milky Way will produce a drastic local enhancement. And as a result, that's why we even see variations of a factor of 2 or 3 in sun-like stars in the total content of our process. And we have advocated here that maybe you need to add, a term into the Drake equation that tells you, what is your R process content in order for habitability to be effective. And I'll stop there and thank you for your time.
Thank you so much. I'm going to do everybody the favor of not clapping into a terrible microphone. It sounds horrible, but I'm clapping in spirit. I love that you touched upon the Drake equation, because that's exactly what I was thinking right when you were finishing up your talk was, okay, so then for the people that are searching for, planets outside, exoplanets, et cetera, these searches, are they taking this into consideration? And it sounds like maybe the answer is yes, they should, and they might. Great, thank you so much. Okay, so then I'll open it up to questions. Please feel free to raise your hand. You can also write it in chat. I am also monitoring chat. Let's see. Okay, yes, they're coming in now. Ed? Feel free to unmute, Ed. 'Cause Unfortunately, we're still not getting any audio from you. I'm not sure what's going on there. Feel free to type what you were going to type into the chat, and I'll make sure to ask for you. But you can keep also working on the audio to see what's going on. But I'm not even getting any kind of activity on the mic, unfortunately, Ed. Okay, so then Ilan?
Can you hear me?
Yes, I can hear you, Ilan.
Very short. I am not in the field completely, but how you describe interestingly the R processes. I recall that people were talking also about P processes. Are they of any significance in spite of on top of the S?
Yeah, I think that there's lots of interesting discussion about I and P processes, but they don't contribute significantly at these heavy for these heavy elements.
Thank you, Ilan. Alex Filipenko in the chat says, in the Drake equations, lots of things are left out or more accurately subsumed into the term suitable stars. For example, the presence of a large moon. Okay.
Yeah, certainly life is much more complicated than that.
Always.
But it was interesting to us that you know, we were excited when we realized that these R process elements are really driving the heating rate of the Earth today, and you know, or preliminary calculations show that it may have, you know, strong consequences to the creation of a magnetic field. But I agree with you that there's lots of things that we left out, and that we probably don't realize as human species, you know, how lucky we are to have the Earth that we have and how much we should take care of it.
Yeah, exactly what I was thinking as well. Thank you. One anonymous attendee asks in the Q&A, and this might be a tall ask because we just talked about a few of these things, but can you describe a little bit more in more detail how you would be able to incorporate this type of work into the Drake equation? And I guess the heart of it would lie into what you were just talking about, which is these kind of elements, the abundance of those elements in the core of the Earth, to be able to allow for magnetic fields to be built, etc. Let me see. But yeah, Enrico, I don't know if you have any kind of insights to how you would be able to include this into you know, the Drake equation, this kind of work.
Yeah, I think what we're trying to understand, especially these calculations are very preliminary and they're just in one dimension, is, you know, there's basically a balance of heating and cooling in the Earth, and you know, how those boundary conditions ultimately affect the formation of the magnetic field. So the question is, you know, depending on what we will do is, for example, if we show that if you have, you know, more than 50% difference with the current R process content of the Earth, and that makes it not effective to actually produce life, then what you can go and, you know, is try to accurately measure the R process contents of stars, you know, around the metallicity of our own sun, and then say, you know, what fraction of those are above, what fraction of those are below, and basically, you know, what fraction of those lie within a region where we think is effective to actually generate a magnetic field. Now, there are significant amount of challenges to actually measure the R process contents of stars with that amount of accuracy, and there's some systematic effects that go from how you go from the absorption, you know, the depth of the absorption feature ultimately to the total amount of mass. That's, I think, how people think of proceeding. No, it's almost the same kind of argument of, you know, how many sun-like stars have Earth-like planets at a distance where, you know, water can exist in liquid form. You will do the similar calculation in terms of the fraction of stars that are within the heating rate that we think will be effective to generate a magnetic field.
Right. Thank you. Once again, it's highlighting the kind of extremely specialized conditions that gave us where we are now. I want to get to Ed's question because I know it's had trouble with the sound. He says, "Are you saying that R processes generate mass? If so, how?"
Yeah, certainly mass is conserved. And what it does is that you have a huge amount of neutrons, and you already have the targets, as we show, particularly in the first peak in nuclear statistical equilibrium. Those basically few neutrons are captured and build, progressively heavier elements.
Right. Great. In the Q&A, I've got one from Wick Axon. It says, Enrico, great talk. Your European results and your concluding argument reminded me of an argument by, I'm going to butcher this, Young Chan, that the statistics of European enrichment, the lack of large fluctuations in old metal poor stars, argued for a frequent R process at that time. Thoughts?
Yeah, so I think there's two aspects of it. I think there are aspects of the first peak. So certainly the RMS fluctuations of the first peak are rather different than the second and third, and we don't see correlations between the first, second, and third peak. So I think the first peak is certainly consistent, and the arguments that I show you about minimum mass estimates are actually in line with our argument that the first peak can actually be produced by some sort of standard core collapse supernovae whose entropy was maybe not high enough to actually get to the second and third peak. But certainly what we see is that the abundances in these low metallicity stars, especially in europium and the heavy R process, are incredibly large, are almost a factor of 5 to 10 times larger than what we see for alpha elements, which immediately tells you that if they were both coming from the same source, they will have to have the same, RMS fluctuation. So that's what points to the rarity.
Thank you. And then we have one more in the chat, and I think we might have time for one more question on top of that, or maybe we'll end it there. From Alex, he asks, even though, let me see, hold on, it's a little bit up. So just to be clear, some R process elements may be produced primarily by weird CC supernova, even though most are produced by merging neutron stars. That's where you get the most of the mass from. Actually, oh, never mind. No, no, I'm reading in real time. Actually, he just answered my question with a similar tweet. Thank you, Alex Filipenko.
Yeah, and I think, Alex, some of the debate that we currently are having is, neutron star mergers take a little bit of time to merge because you have to assemble them and then merge them. So they may be a delay of about 100 million years unless you find a fast merging channel. So there's a significant amount of debate as to whether or not that 100 mega year delay is too long so that you won't be able to enrich the gas early on, and therefore you require, as you were saying, some sort of exotic weird core collapse supernovae that produce a significant amount of R process. So I think the debate is all about really trying to understand the injection of metals, where those metals are injected, and how they're mixed. In addition, as you know, neutron star binaries get a kick in formation, so they move relatively far from their place of birth, and therefore they deposit their elements farther away from the disk. So that element has to come back, cool into the disk, and form new stars. And right now, different simulations with different resolutions are giving different results. So.
Okay, but the relative rarity is what really also drives the mass limits, or the minimum mass ejected. Great. Okay. One last question, or I'll give it a few seconds. Okay, great. I think that's enough for a slow internet connection to get their point across. Okay, so then we'll close it out. Thank you everyone for attending the first colloquium talk. There'll be more to come, so keep your eyes on the email. And thank you so much. A special thanks to Professor Enrico Ramirez Ruiz for this wonderful talk. We appreciate it. And thank you for coming, everyone. Have a great day.
Thank you, Cesar. Thank you, Compass, for inviting me. A pleasure being here.
Thank you. Bye, everyone.